Hello everybody, my name is Yanting Ma. In this video, I'm going to introduce our work on multiview sensing with unknown permutations, where we solve the problem using an optimal transport approach. This is joint work with Petros Bofanos, Pascal Mansour, and Sujin Aaron. The problem that we are considering here is to reconstruct an object measured through a linear system while the object is in motion. For example, we may think of in vivo coherent imaging of a beating heart or a breathing lung, and radar imaging of people walking. As an illustrative example, let's suppose that the letter E on the top is the object to be reconstructed. As it moves, it is measured in a sequence of frames. Due to the motion, it undergoes a series of deformations which determines its pose in each frame of the measurements. In this work, we assume that we have a motion tracking system that can roughly predict the motion of the object, and the difference between the predicted motion and the true motion can be represented by a permutation matrix. In other words, the permutation matrix corrects the error made by the motion tracking system. Specifically, we assume that xi equals to pi fix, where fi is the predicted motion operator and pi is the unknown permutation. We further assume that the error from the motion tracking system is less likely to be non-local. And since the permutations are used to correct the tracking error, this is equivalent to assuming that the permutations that move pixels far away from its original position on the underlying grid where the signal is defined are less likely. We're now ready to introduce our proposed method for solving the imaging problem. First, we define a cost function consisting of a quadratic data fidelity term and a regularization term for the permutation matrix, which should reflect our assumption about the permutation. And we also include the constraint xi equals to pi fix based on our assumption that the motion tracking operator fi is correct up to a local permutation pi. Of course, one can also include regularizations for the object x based on the specific problem on hand. Since this is not the focus of this work and can be easily incorporated into our method, we will leave it out in this video. Instead, we focus on the regularization for the permutation. The one that we define here is the weighted sum of all the entries of the permutation matrix, where the weight for the n entry is the distance between the nth and the n pixel on the grid. Essentially, this will penalize permutations that move pixels far away on the grid, matching our assumption. While this is a reasonable formulation, the computation is very expensive, since it requires a combinatorial search over a set of n by n permutation matrices. In order to make the problem tractable, we will relax the equality constraint and relate it to the optimal transport problem, for which many efficient off-the-shelf algorithms are available. Specifically, we first relax the equality constraint to penalizing the squared L2 norm between the true motion and the predicted motion after the permutation correction. Then, after some basic manipulation, we can rewrite the relaxed problem in this new form. We notice that pi is no longer constrained to be in the set of permutation matrices, but is obtained through an assignment problem, in which the optimal solution is a permutation matrix. The assignment problem is a special case of the optimal transport problem, which can be briefly described as follows. Given two marginal distributions, u and v, we want to find a joint distribution p, also known as the optimal transportation plan, with marginals u and v, such that the cost of moving the mass is minimized. Note that the choice for ui-vi being uniform is to ensure that the optimal joint distribution pi is a permutation matrix. In our case, we only care about the reconstruction of x but not pi, so we can choose different marginals. We further notice that the gradient of the OT term with respect to x and xi can be computed conveniently using the envelope theorem. So we use alternating minimization to alternate between the estimation of x and xi, where each subproblem is solved by gradient descent. In each iteration, we let ui and vi be uniform over the support of xi and the fix, and the zero of the support. Now, to see how well our method performs, we compare it with two baseline methods. The first one is labeled as gradient in the plot, which relaxes the permutation constraint to penalizing the column sum and the row sum of the matrix being different from 1 by a differentiable term, so that the gradient method can be directly applied. The second baseline approach simply ignores pi, assuming that the motion tracking system is perfect. From the plot, we can see that our method outperforms the baseline methods at all tested measurement rates and all measurement noise levels. As a concluding remark, we demonstrated via simulation results that we can use optimal transport to solve a seemingly intractable problem, which has numerous applications in the research areas to explore. Thank you very much for watching. If you have any questions, please contact me through email.